The 1973 Stanford Torus Detailed Design. Chapter 1, The 1973 Blueprint, Beyond the Idea. Host, welcome back to Synapse Daily. Today, we are opening a very specific vault. We aren't talking about maybe. We are talking about the manual. In 1973, NASA Ames Research Center and Stanford University decided to stop daydreaming and start calculating. The result was a massive technical publication titled NASA SP413, also known as Space Settlements, a design study. This was a monumental shift in human history. For the first time, the space colony transitioned from a science fiction trope into a rigorous, data-heavy detailed design. Why 1973? The context is everything. The Apollo program had just concluded, leaving NASA with world-class engineers but no destination. Simultaneously, the global energy crisis was making everyone realize that Earth was a closed, fragile system with limited resources. NASA didn't just want a space station, they wanted an orbital infrastructure that could solve Earth's problems. The SP413 document is a 200-page masterpiece of engineering. It covers everything from the thickness of the aluminum hull to the specific amino acid requirements of the residents. It was the first time a group of top-tier scientists looked at the void and said, "Here is exactly how many bolts we need." This wasn't about exploring the unknown, it was about building the known. In this chapter of the detailed design, NASA laid out the prime objective, to design a permanent, self-sustaining community for 10,000 people using 1970s technology. They didn't assume warp drives or magic gravity. They used the physics available in 1973. The Stanford Torus was born from the realization that we don't need new physics to live in the stars, we just need a very good construction plan. As we dive into these pages, remember, every number we discuss was vetted by the same agency that put men on the moon. This is the blueprint for the city that almost was. Chapter 2, The Geometry of Gravity, 900 Meters to Heaven. Host, let's talk about the ring's skeleton. The most iconic feature of the 1973 design is its shape, the torus. But the dimensions weren't chosen for aesthetics, they were chosen for the human inner ear. NASA's engineers faced a brutal constraint, human biology. We evolved in 1G. Long-term exposure to zero gravity leads to bone loss, muscle atrophy, and immune failure. To live permanently in space, you need gravity. Since we can't generate gravity, we have to simulate it through rotation. The 1973 detailed design settled on a major radius of 900 meters. To get to this number, they had to balance two opposing forces. If the ring is too small, you have to spin it very fast to get 1G. But if you spin faster than 1 revolution per minute, humans start to suffer from Coriolis-induced motion sickness. Basically, if you turn your head too fast in a high RPM station, your inner ear goes haywire, and you vomit. By choosing a 900-meter radius, NASA allowed the station to spin at a gentle 1 revolution per minute while providing a rock-solid 1.0 G at the outer rim. This is the Goldilocks zone of space architecture. The living tube itself, the donut part, was designed to be 130 meters wide. This provides a massive internal volume. NASA calculated the tensile stress on the aluminum hull at 101.3 kilopascals. That is the exact pressure of Earth's atmosphere at sea level. The design was so detailed that it accounted for the hoop stress of the air trying to explode the ring outward into the vacuum. To build this, they specified the use of aluminum alloy 2219, a material they knew well from the Saturn V rockets. It was strong, weldable, and, crucially, could be refined from moon rocks. This was the first time we designed a city where the geometry was dictated by the very shape of our balance and our breath. Chapter 3, The 5 Million-Ton Shield, Lunar Regolith. Host, space is a shooting gallery. Without Earth's magnetic field and thick atmosphere, a human in orbit is exposed to constant, lethal doses of cosmic rays and solar flares. In the 1973 detailed design, NASA solved this with the most heavy-duty solution possible, 5 million tons of moon dust. NASA SP413 didn't rely on thin lead sheets. They calculated that to reduce radiation to a safe level, defined as less than 0.5 rem per year, you needed a barrier equivalent to several meters of Earth's atmosphere. Their solution was a non-rotating shield made of compressed lunar regolith, lunar soil. Imagine the structure: the living ring is spinning at 1 revolution per minute, but just centimeters away, a massive, stationary tire of moon bricks surrounds it. This shield doesn't spin. This is a critical engineering detail. If you tried to spin 5 million tons of soil, the structural requirements would be impossible. Instead, the living torus floats inside this stationary fortress. How do you get 5 million tons of dirt into space? The 1973 report details the mass catcher at the L2 Lagrange point. Robotic miners on the moon would bag the soil and sling it into space using an electromagnetic railgun. These bags would be caught and transported to the construction site. The soil would then be sintered, melted by solar furnaces, into thick bricks. The resulting shield was 1.7 meters thick. This wasn't just a wall, it was a planetary defense system. It made the Stanford Torus the safest place in the solar system. Even a direct hit from a solar superflare wouldn't penetrate this lunar fortress. NASA proved that by using the moon's waste material, we could build a bunker that felt like a valley. Chapter 4: The Spokes in the Hub, 6 Veins of Steel. Host: a ring floating in space is useless if you can't get into it. The 1973 detailed design treated the Stanford Torus not just as a habitat, but as a transportation hub. Connecting the outer living ring to the central axis were 6 massive spokes. Each spoke was designed to be 15 meters in diameter. That's wider than a Boeing 747's fuselage. These aren't just support beams, they are the veins of the city. They contain high-speed elevator systems, air ducts, and power lines. The engineering of these spokes is fascinating. As you travel from the hub toward the rim, the gravity slowly increases. At the center, the hub, you are in zero gravity. At the rim, you are in full gravity. The elevators had to be designed to handle this weight gain during the transit. But why 6 spokes? NASA's structural analysis showed that 6 provided the perfect balance between stability and mass. They act as tendons, keeping the spinning ring from deforming under its own centrifugal force. At the very center of the wheel sits the central hub. This is the only part of the station where ships dock. Because the hub is on the axis of rotation, the relative velocity for a docking ship is almost zero. It is a non-rotating docking cylinder. The 1973 report goes into extreme detail about the bearing system that connects the rotating spokes to the non-rotating hub. They proposed massive mechanical seals and electromagnetic bearings to prevent air leaks while allowing the station to spin indefinitely. This was the Grand Central Station of the High Frontier, a place where the physics of the spin met the stillness of the void. Chapter 5: The Chevron Mirror System, Optical Engineering. Host: how do you bring sunlight into a windowless, lead-shielded bunker? You can't just cut a hole in the hull, the radiation would be lethal. The 1973 detailed design solved this with one of the most elegant optical systems ever conceived, the Chevron mirrors. Above the spinning torus, NASA placed a giant, stationary primary mirror. This mirror, hundreds of meters wide, is angled to catch the sun 24/7. It reflects that light down toward the ring. But here is the genius part: the light doesn't go straight in. It hits a secondary system of mirrors called chevrons. These are V-shaped, zigzagging slats made of aluminum and backed with heavy radiation shielding. Imagine a Venetian blind made of mirrors. Visible light, the good stuff, hits the silvered surface and reflects perfectly around the corners into the habitat. However, cosmic rays, X-rays, and high-energy particles travel in straight lines. They can't turn the corner. They hit the back of the chevron slats, which are lined with lunar slag, and are absorbed instantly. The 1973 report calculated that this system would deliver 10,000 lumens per square meter, the exact intensity of a bright spring day on Earth. But it wasn't just about brightness. By tilting the primary mirror, the station administration could simulate a 24-hour day. They could create a slow, orange sunrise, a bright midday, and a soft, purple twilight. They even design. Chapter 6: The Bioengineered Interior, Hectares and Scrubbers. Host: now, let's talk about the breadth of the machine. How do 10,000 people stay alive in a sealed tube for decades? In the 1973 detailed design, NASA moved away from sci-fi canisters and toward a massive, hyper-integrated biological life support system. The report specifies exactly 63 hectares, about 155 acres, of intensive agricultural space. This wasn't a scenic garden, it was a high-output calorie factory. NASA's engineers calculated that to sustain 10,000 people, the colony needed to produce 2,400 calories per person, per day. But in space, you don't have the luxury of traditional farming. They designed a multi-tier vertical farming system. Because the sunlight from the chevron mirrors is constant, the plants could grow 24 hours a day in CO2-enriched environments. The report suggests maintaining CO2 levels at roughly 1,500 parts per million, nearly 4 times higher than Earth's, to turbocharge photosynthesis. Under these conditions, a single hectare in the torus could produce as much food as 5 hectares on Earth. But the most revolutionary part of the 1973 design was the waste management. NASA proposed a process called wet oxidation. Instead of traditional sewage treatment, all organic waste, human waste, kitchen scraps, and inedible plant matter would be fed into high-pressure, high-temperature reactors. This process breaks down waste into pure water, carbon dioxide, and sterile ash rich in nitrogen and phosphorus. This ash was then cycled back into the agricultural tiers as fertilizer. This was the world's first blueprint for a 100% closed-loop ecology. Every atom was tracked. The water you drank in the morning was the same water that had transpired through a wheat stalk the night before. NASA proved that with enough engineering, a small ring in the void could be more fertile than the Nile Delta. Chapter 7: Thermal Radiators, Chilling the Ring. Host: Here is a technical reality that most people forget: space is the perfect insulator. In a vacuum, there is no air to carry heat away. Between the constant 24/7 sunlight, the body heat of 10,000 residents, and the massive electronic systems, the Stanford Torus had a fever problem. NASA's 1973 thermal analysis was brutal. Without an active cooling system, the temperature inside the living tube would skyrocket to over 100 degrees Celsius within just a few days. The colony wouldn't freeze, it would slow cook. The detailed design solved this with a gargantuan external radiator system. Imagine giant, thin aluminum fins extending from the non-rotating shield into the dark. These radiators were designed to be hundreds of meters long. They used a closed-loop coolant system, likely using water or a specialized Freon-type liquid that would absorb heat from the interior air and pump it out to these fins. Once in the fins, the heat is radiated away as infrared radiation into the deep freeze of the universe. The math in the SP413 report is incredibly specific about the view factor of these radiators, meaning they had to be positioned so they didn't see the sun or the warm parts of the station itself. They also designed the interiors weather-based on this thermal load. By controlling which parts of the radiators were active, the station's computers could create temperature gradients. This would generate internal winds, preventing the air from becoming stagnant. It's a masterclass in thermodynamics. In the Stanford Torus, the breeze you feel on your face is actually the sound of the station's life support system dumping calories into the void. Chapter 8: The Industrial Hub, Zero-G Manufacturing. Host: Why spend billions on a ring in the sky? NASA's 1973 report wasn't just a housing plan, it was a business prospectus. The detailed design envisioned the torus as the industrial capital of the solar system. At the very center of the hub, the report details a massive manufacturing zone. Because this area is on the axis of rotation, it experiences zero-G. For an industrial engineer, this is paradise. The 1973 design focused on 2 main products: solar power satellites, SPS, and exotic materials. The plan was to use the torus as a construction shack. The 10,000 residents would spend their shifts building enormous solar arrays, kilometers wide, which would then be moved to geostationary orbit to beam clean energy back to Earth. But the zero-G hub also allowed for containerless processing. On Earth, gravity causes impurities to settle in molten metal or glass. In the torus hub, you can melt materials in mid-air using acoustic or electromagnetic fields. This allows for the production of perfect ball bearings, ultraclear fiber optic cables, and massive silicon crystals for electronics that are impossible to grow under Earth's 1G pull. The 1973 report even calculated the return on investment, ROI. They argued that by manufacturing these high-value items and satellites in space using free lunar materials and solar energy, the Torus would not only pay for itself but would spark a second industrial revolution. It was a vision of a world where Earth is for living, and space is for the heavy lifting of civilization. Chapter 9, The Village Design, Low-Density Sociology. Host, NASA's architects in 1973 were deeply worried about the submarine effect. If people felt like they were living in a military base, they would eventually go insane. So, the detailed design for the interior wasn't inspired by high-tech labs, but by Mediterranean villages. The report specified a low-density residential plan. No high-rise apartments. Most houses were designed to be no more than 3 or 4 stories tall. They used the natural upward curve of the ring to hide the end of the world, creating a sense of an infinite horizon. One of the most impressive technical details in this chapter is acoustic dampening. In a metal and glass cylinder, sound bounces. NASA's engineers realized that a city of 10,000 would be deafeningly loud if not managed. They designed the interior with specific sound buffers, belts of trees, rolling hills made of lunar soil, and textured building surfaces to break up sound waves. The design also included microclimates. Because the ring is so large, different sectors could have slightly different temperatures or humidity levels. One village might feel like a misty morning in San Francisco, while another feels like a dry afternoon in Tuscany. They even planned for social redundancy. By breaking the 10,000 people into smaller neighborhoods, they aim to foster a sense of community accountability. In a closed loop, your neighbor isn't just a person next door, they are the person responsible for the air you breathe. The 1973 design proved that to build a successful space colony, you have to engineer the heart just as carefully as the hull. Chapter 10, The Legacy of the 1973 Blueprint. Host, as we conclude our deep dive into NASA SP413, we have to face a startling truth. Everything we have discussed, the 1 revolution per minute rotation, the lunar shielding, the chevron mirrors, and the wet oxidation, is still scientifically valid. When NASA published the Stanford Torus detailed design in 1973, they didn't just give us a dream, they gave us a ready-to-build project. The math for the structural integrity holds up. The chemistry for lunar refining is sound. The logistics of the L5 point are unchanged. The legacy of this report is that it removed mystery from space colonization and replaced it with logistics. It showed us that the only thing standing between humanity and a multiplanetary existence isn't a lack of brilliance, it's a lack of collective will. Today, as we see companies like SpaceX and Blue Origin lowering the cost of orbit, the 1973 blueprint is being dusted off. Jeff Bezos has openly cited these studies as the inspiration for his vision of millions of people living and working in space. The 1973 design is no longer a relic of the past, it is the starting line for our future. NASA proved that we can build an Eden in the void. They proved that the moon is our quarry and the sun is our engine. All we have to do is decide that the Earth is a cradle we have finally outgrown. Thank you for joining us on Synapse Daily for this technical journey. Next time you look at the moon, don't just see a rock. See the bricks of your future home.